Welcome to the second of 3 videos about solving limits. This method is known as solving limits analytically or algebraically. I've heard it both ways. And this method is the one you will probably use the most for solving limits problems. So this is where we really kind of get into the meat of solving limits. And it's not too bad. There are several steps to remember, but it's really not too difficult. But since there are several steps, we're going to go ahead and dive right into it. There are 3 sub-methods to solving limits analytically. The first is direct substitution, and I'll go over each of these in depth. The second is cancellation, and the third is rationalization. And you can kind of think of these as a plan A, a plan B, and a plan C. So you always want to try direct substitution first. And if that doesn't work, you try plan B, cancellation. And if that doesn't work, you try plan C, which is rationalization. And ultimately, you always want to end up doing direct substitution. This will make more sense when we actually solve the problems. But if you can just do plan A, direct substitution, right off the bat, great, you're done. But if you can't, you use cancellation to get to the point where you can then use direct substitution. And if you can't do that, you do the same with rationalization, where you can then use direct substitution. And again, this will make more sense once we actually start going over these methods in depth. But just for now, know that there's a plan A, a plan B, and a plan C. And the goal is to always get the problem to where you can use direct substitution, your plan A. Let's dive right into the first method, direct substitution. And remember, this is our plan A, and this is the one that we're always trying to go back to using the other methods. And luckily, it's really easy. So for direct substitution, you literally just plug in A for f of x. So the limit of f of x as x approaches A is just f of A. And this is almost always true, right? The graphs we were looking at in the previous videos, this tended to be true. It might not be true if you have something like a piecewise function where the value at A jumps and doesn't fit into what the normal function looks like, but that's pretty rare. Usually, if the function exists at x equals A, the limit as x approaches A will just be f of A. So you're just going to plug in A for f of x. Let's look at a quick example. The limit as x approaches 3 of 4x squared minus 8, and we're just going to plug 3 right in for x. So that's going to give us, just do some really quick algebra, and that's going to give us 28. So the limit as x approaches 3 of 4x squared minus 8 is 28. And that's direct substitution. You just plug A right in for x. The second submethod is cancellation. And again, this is our plan B. So this one is pretty straightforward as well. All you do is, if you cannot do direct substitution at first, you see if there's some factoring you can do. So you factor the numerator and the denominator, and you hope that there's a common factor in the numerator and denominator that you can cancel out. So once you do that, you then try direct substitution again. So you factor numerator and denominator, cancel out the common factor if there is one, and then you use direct substitution. Let me show you an example. What is the limit as x approaches 2 of x squared minus 4 over x squared plus x minus 6? Remember, we always try our plan A first. We always try direct substitution first. So let's plug in 2. We get 2 squared minus 4 over 2 squared plus 2 minus 6. And that equals 0 over 0, which makes us really sad because we can't do anything with that. And now we know since direct substitution didn't work, we have to resort to our plan B, cancellation. So step 2 is when we actually do the cancellation. And remember, we are going to factor the numerator and the denominator and then cancel out the common factor. So x squared minus 4 over x squared plus x minus 6. If you remember from algebra, x squared minus 4 is the difference of 2 squares. That factors to x plus 2 times x minus 2. X squared plus x minus 6, that factors to x minus 2 times x plus 3. So the x minus 2's cancel, and then we are left with x plus 2 over x plus 3. So that is the simplified version of this function. For step 3 of this method, we are going to try direct substitution again. So we are going to plug in 2 into our now simplified function. So we plug in 2, we get 2 plus 2 over 2 plus 3, and that equals 4/5. So that's a good number, right? That's not a 0 over 0. 4/5 is an actual number. So that means that we've solved it. We can now come over here and say that the limit as x approaches 2 of x squared minus 4 over x squared plus x minus 6 equals 4/5. And so that's the cancellation method. We first tried direct substitution. It didn't work. We factored out the numerator and the denominator, and we found a common factor, canceled that out, and we got a simplified version of the function, and then we plugged in a for x again, and we got an actual answer. So that's cancellation. Our third submethod is called rationalization, and again, this is our plan C. So you will use this if plans A or plans B don't work. Also, this one deals with radicals really well. So if you see some radicals in your limit, there's a good chance that you're going to end up using rationalization, especially if the radicals are in the denominator. This method uses something called the conjugate. So I'll really briefly describe what that is. It's very simple. The conjugate of a plus b is a minus b, and the conjugate of a minus b is a plus b. It really is that straightforward. Step 1 of the rationalization method is to locate the radical. And a lot of times, to be confusing, these problems will probably have several radicals, but the ones you're interested in are the radicals that are involved in a sum or a difference. Step 2 of the rationalization method is to multiply by the radical's conjugate divided by itself, which really is just a clever form of 1. So you can multiply anything by 1 and it doesn't change it, right? So you're essentially multiplying by like 4 over 4 or 12 over 12. It's just a really clever form of 1 that will help you solve the problem. So the radical's conjugate divided by itself. And this will make more sense once we actually dive into an example. Step 3 of the rationalization method is you simplify the numerator, but not the denominator. So for the numerator, you multiply it all the way through, and denominator, you just leave as the product. And you'll see what all this means once we actually do an example. But once you've done this, you can then typically cancel something out to make it so that direct substitution will work. And again, you'll see what this means when we work with an example. But remember, we're always trying to get back to the point where direct substitution works. So you simplify the numerator and not the denominator, and then you cancel something out, and then direct substitution will typically work at that point. Let's look at an example. The limit as x approaches 0 of the square root of x plus 2 minus the square root of 2 divided by the square root of x. As always, for step 1, we try direct substitution first. So let's just plug in 0. So we get the square root of 0 plus 2 minus the square root of 2 divided by the square root of 0, and that equals 0 over 0, which makes us sad because we can't do anything with that. So for step 2, we go to plan B. We try to do cancellation, but we look at that function and nothing's factorable. So we can't do cancellation. So we have to go on to plan C, rationalization. The first step for rationalization is we have to identify our radical. And remember, we're looking for the sum or difference of radicals. And we see that in the numerator, the square root of x plus 2 minus the square root of 2. So that's our radical. The next step is to identify the conjugate of the radical. Since here we have the square root of x plus 2 minus the square root of 2, the conjugate is just going to be the square root of x plus 2 plus the square root of 2. It's that easy. Next, we multiply our original function by the conjugate divided by itself, which is, again, just a little sneaky form of 1. So we multiply the square root of x plus 2 minus the square root of 2 divided by the square root of x. That's our original function. We multiply that by the square root of x plus 2 plus the square root of 2 divided by the square root of x plus 2 plus the square root of 2. And if you, again, look at that second term, that's 1. That's just something divided by itself, so we're just multiplying the function by 1. And now we simplify. Remember, we multiply the numerator all the way through, but we leave the denominator as is. So multiplying the numerator all the way through, that gives us x plus 2 minus 2, divided by the denominator, which we leave as is, which is the square root of x times, in parentheses, the square root of x plus 2 plus the square root of 2. And we simplify the numerator one step further, and we just get x divided by the square root of x times the square root of x plus 2 plus the square root of 2. And now here's where we cancel a little bit. We have an x in the numerator and a square root of x in the denominator. And that simplifies to just be the square root of x in the numerator. So we simplify this one step further and get the square root of x divided by the square root of x plus 2 plus the square root of 2. And now the reason we don't simplify the denominator is because the denominator is the reason that we have to do this in the first place, right? We had a square root of x in the denominator. And so when we plugged in 0, it didn't work, right? We had a 0 in the denominator, and you can't do that. You can't divide by 0. So we have to get rid of it somehow. And so that's why we leave it as is, because we're hoping that we can cancel out that square root of x. And using this conjugate method, that helps us do that. And now we can go back to direct substitution. So we just plug in 0 to our new simplified function. So the square root of 0 divided by the square root of 0 plus 2 plus the square root of 2 gives us 0 over 2 radical 2, which is just 0. So we're done now, right? So the limit as x approaches 0 of the square root of x plus 2 minus the square root of 2 divided by the square root of x equals 0. Let's recap, because we covered quite a bit. There are 3 sub-methods to solving limits analytically, and you try them in this order. First, direct substitution. And for that, you just plug a into the function. If that doesn't work, you try cancellation. For cancellation, you factor the numerator and denominator, you cancel out the similar term, and then you go back to direct substitution. Type 3 is rationalization. You find the sum or difference of radicals, you multiply by the conjugate divided by the conjugate, simplify the numerator only, cancel whatever you can, and then you go back to direct substitution. And you'll notice most of what we've been doing so far is just kind of fancy algebra. And you'll notice that with calculus by and large. Most of calculus is algebra followed by one step of calculus and then more algebra. So if you're comfortable with algebra, calculus really isn't that bad. If you found this video helpful, please share it with your friends, like this video, and subscribe, and I will keep the math content coming.